Welcome to the last section in Chapter 9. This section is all about optimizing. It's about finding the vertex. And the vertex is a new word. You won't have heard that in Math 100 in beginning algebra. So we're going to start just by looking at the relationship of the square. So this first example is asking us to graph, that is to give a visual representation of the relationship between y and x squared. We're asked to graph the equation y equals x squared. And we're going to do this exactly the way a calculator does to begin with, just to introduce this new idea. So what we're going to say is, let's make a table. Calculator makes a table a pixel wide. We're going to make a table an integer wide. We're going to start with x equals 3, and we're going to ask the question, what happens to x when you square it? In other words, what do you get for y when you square 3? And of course the answer is you get 9. So when x equals 3, y equals 9. We can plot that point and ask the next question. The next question asks when x equals 2, what's y? Well, our equation says to square that x, so in this case we're squaring 2. That gives us the square of 2, namely 4. And we're continuing this way. We now have 2 points. That first point, that first ordered pair, if we interpret it geometrically, we can think of it as a point, is x equals 3, y equals 9. The second point, x equals 2, y equals 4. And we're going to continue in this way. So we ask the question, what is y when x is 1? Well, 1 squared is 1. So now we have a third point. And we continue in this way. When x is 0, we square it, and that gives us 0 for y. Now be very careful about negatives. We're asked to square -1. Now that means that if we were drawing this, if we were writing this notation, we would have to put the -1 in parentheses so that the 1 and the negative both get squared. So -1 squared, of course, is -1 times -1, and there's our 1 again. Now something interesting about 0, 0 in this example, and that is it looks like we're seeing some symmetry. In other words, above 0 at +1, we're getting the same y value as below 0 at -1. So let's continue in this way. Remember, when we square -2, we multiply the -2 times a -2. That gives us a 4 again. And when we square -3, we get a 9 again. Something very special is happening in this example at the point 0, 0. That symmetry is what we're talking about, and that gives us the word vertex. Now, when we plot these points, we do that exactly the way you'd expect. So this first point, 3, 9, the first point we found, is out here at x equals 3 and y equals 9. So we put a point there. And then similarly, we put a point at 2, 4. X equals 2, y equals 4, and we plot that point. And we continue in this way. So we plot all of these points, and then we connect it with a nice smooth line. Now, if you were doing this in class, or if you're taking a class later on and you're asked to graph parabolas, 2 things that I look for when I'm grading an exam with a parabola in it. So the first is a nice smooth curve around the vertex, around that point of symmetry there at 0, 0 in this example. Nice smooth curved, bent, not broken. So something you could roll along, not something sharp, not something broken. And the other thing that I look for when I'm grading these is that the curve goes up, in this case, and out, right? It's not going vertically. It's going up, and it's also going out. So that part going out is very important. Okay, you're not going to have that issue because you're going to enter these into the computer and it'll draw a beautiful parabola for you. Just to recap, the new big idea here is the vertex. I used the word symmetry. That symmetry is the idea that if I folded this graph along that axis of symmetry that goes through the vertex, I'd see a mirror image. In other words, if this was painted with goopy paint on one side, I could fold it along that line and through the vertex, and I'd get a mirror image of that curve. So the big idea here is the vertex. Let's look at another very similar example. Here's an example very much like the previous one, except there's a little bit more arithmetic. And of course what we mean by that is we've got to do 3 things to our x to get y. This tells us to do 3 things. It tells us first to square, then change the sign. So square and then change the sign, but then of course the last thing after squaring and changing the sign is adding 4. So that's just what the order of operations, what the arithmetic says to do. So let's talk through this. This first case, we're going integer by integer, just brute force. This doesn't always produce a graph, but it does enough of the time. So it's saying x equals 3. We're supposed to do 3 things to that. Square it, change its sign, and add 4. You square 3 and you get 9. You change its sign and you get -9. You add 4 and you get -5. So we'll see the -5 when we put in x equals 3. Now we're going to continue doing that. The rule stays the same. It says square, change the sign, and add 4. So we're going to plug in an x equals 2 now. When we square it, we get 4. We change the sign and get -4. We add 4 and we get 0. And so now we've got 2 points. Let's keep on going. When x equals 1, we're going to square it. That's 1. Change its sign, -1. Add 4 and get 3. Now, we don't see any symmetry in these numbers yet, so we're going to keep on going. X equals 0. Square it, you get 0. Change its sign, still 0. Add 4 and you get 4. So we're just working through the arithmetic using the rule, the order of operations to do this. You could do this in a calculator. -1 squared, of course, is +1. Change its sign, you get a -1. Add 4 and you get, my goodness, is that a 3 again? So we are starting to see that vertex appearing. Those 2 3s on either side of that 4 it kind of implies to me, and when I'm teaching this in a lecture class, I'll say, hey, what do you guess is next? And a little glance at this probably convinces you that we should get a 0 for y next, and that's exactly right. -2 squared is 4. Change the sign on 4 and we get -4. -4 plus 4 is 0. So there's our 0. And then last but not least, we plug in the -3 and we get the -5. So we go through exactly what we did before, that is plotting all of these points. So all of these ordered pairs give us points. So for example, the point 3, -5 is right here. X equals 3, y equals -5. So we plot the points and then we connect them with a nice smooth line. And I'll just quickly say bent, not broken, U-shaped, not V-shaped around the vertex. And then at the edges, or at the edge of your graph, still going out, in this case down and out, but going out, not vertical, so going out. So you're going to be able to graph these electronically in MyOpenMath, so that's going to be relatively easy. So the next thing we're going to look at is finding the vertex from a formula. Your book derives it for you. I'm just going to use it. So that's where we are now. Okay, on the next page we're looking at another example, and we could graph this if that was our only objective, just by making a table and filling in points and doing what we did on the previous page. But what we're far more interested in here is learning something about the characteristics of this graph. When I give you a line in y equals mx plus b form, you know 2 things already, the slope and the y-intercept. And that really gives you a lot of insight into how lines work. Their rate of change is the slope, and where they start from is the y-intercept. So we want that same kind of insight about parabolas. So those previous curves with an x squared in it on the previous page, and this graph here, this equation with an x squared in it, no higher exponents, will give us a parabola. So you saw pictures of those, and we're still going to draw them. But we're going to answer some questions about them as we go. So here are some questions. First off, what is the y-intercept? And this is actually exactly like what you do for lines. If someone says to find the y-intercept where a line crosses the y-axis, you're going to say, well, that's neither up nor down. That's where x equals 0. Notice that these aren't lines, they're curves. I'm going to refer to them as parabolas, but we can still plug in x equals 0. And that is an arithmetic question. So literally, we're plugging in x equals 0 into the squared term and the 2x term. They're going to go away, and we're going to be left, no great surprise, with y equals -2. So that's where this curve, this parabola, crosses the y-axis. Now we're going to play that same game with the x-intercept. We're going to substitute in a y equals 0. But pretty quickly you can see that that'll give us a quadratic equation, not a simple numeric answer. So in taking the place of y in the graph that we're asked to make is the 0 that we're substituting in. So this becomes a quadratic equation, and so I'm going to solve this the way you might have seen in Math 100. I'm going to say 1 sum product. The product is -3 and the sum is 2, and my two numbers are 3 and -1. Give yourself a second to convince yourself that that works. 3 times -1 is -3. 3 plus -1 is 2. Now I'm going to factor this using that diamond, so that gives me my two factors, x plus 3 and x minus 1. I'm going to use the zero factor property to get my two x-intercepts at -3 and at 1. Your book refers to this as finding the 5 numbers that make up the parabola, and this is what I'm going to expect you to do as well. Not just plug in some numbers, not use your calculator, but find the x-intercepts and the vertex. Now, very important, this formula for the vertex, and you probably recognize it. You say, yeah, I've seen that before. That's how the quadratic formula starts. The -b plus or minus the square root of b squared minus 4ac all over 2a. Well, we're just looking at that first term in the numerator, -b, and the denominator 2a. And there's good reasons for that. In a lecture class, I'd point those out, but suffices to say we've got a nice, simple formula for our vertex. Now, on the very first example, I said we were interested in optimizing, we were interested in finding extreme values. That's exactly what the vertex is. So this is a very powerful equation. It's a very small equation, but it's very powerful. It tells you when you get to the top of something, and I think we're all waiting to get to the top of the coronavirus right now. So something as simple as -b over 2a basically finds the extreme points, those vertex points. So here's our new formula. We're going to use it throughout Chapter 9. It's going to do all sorts of great things for us. Basically, it just says take out the b, change its sign. That's -b. In this case, our b is +2. So when we change its sign, we get -2. In the denominator, we take 2 times a. So in this case, that means picking out a. Well, of course, a is 1, the coefficient of the squared term. These are the same letters that we use for the quadratic formula. So in the denominator, we've got 2 times 1. So let's see, 2 divided by 2 is 1. A negative divided by a positive is a negative. So the x-coordinate of our vertex is at -1. Now you might say, is there going to be a formula for the y-coordinate of the vertex? And there doesn't have to be. Anytime you're asked to graph a parabola, you're going to be given a formula for y. In other words, y equals, in this case, x squared plus 2x minus 3. So the moment I know an x value, I can plug in that x value to find the y value. And remember, this is all arithmetic at this point because all the x's have become -1s. So we literally just plug it in, we do some arithmetic. Now notice on the previous page I said that if we were squaring -1, we'd have to show it in parentheses. And most calculators out there require you to do that as well. And that's correct mathematical notation. I had to show those parentheses. That's the way that when I square a negative, it's telling the order of operations that the negative is being squared. So -1 squared, when you show it correctly, gives you a +1. In that second term, 2 times -1 gives me a -2, and then of course I'm subtracting 3. So 1 minus 2 is -1, minus 3 is -4. So that's our y-coordinate to the vertex. So the vertex itself is a point. We saw that in the previous two examples. It has an x and a y coordinate. So for our example, the vertex is -1, -4. Now you're probably thinking to yourself that graphing a parabola, which is what I'm kind of asking you to do, is not really the most important part of this question. Well, the important part of this question is knowing what happens to this curve, where it takes on extreme values, and the vertex is exactly that. We are going to graph this, so we're going to take that information and we're going to plot those points. There they are, and we're going to then draw the curve. So that curve is called a parabola. This is an upward opening parabola. It's a smiley parabola. We can see that the coefficient on the squared term is positive. There's a +1 there in front of that x squared if we needed a coefficient. And that tells me that this parabola is upward opening. It's smiling at me. So there's my kind of rough smile there. Upward opening positive parabola. Okay. Okay, one more example of graphing a parabola by finding the x-intercept, the y-intercept, and the vertex. So all sorts of good stuff. So we're going to go through this just a tad quicker. You can always rewind, you can always pause. So again, to find the y-intercept, we plug in x equals 0. Well, there's not a lot left when we plug in x equals 0 because everything's got an x in it as a factor. So that's going to give us y equals 0. There's our y-intercept. Now for our x-intercept, exactly what we did before, exactly what we did when we were talking about lines, linear equations. We're going to plug in y equals 0. Now that's going to give us the quadratic equation taking the place of y is 0. So we expect two solutions. Notice that I don't need a diamond for this. This is relatively easy to factor. There is a common factor of x in both of these terms. There's an x in x squared and there's an x in 2x, so guess what? I'm going to factor it out. So we're using the zero factor property. We've got the 0 from the fact that we're looking at an x-intercept. We factored just by pulling out the GCF, and now we see that there are two x-intercepts at 0 and -2. Notice that the y-intercept is also an x-intercept. That makes sense. It's crossing both axes when it crosses the origin. Now, the vertex is exactly what we saw on the previous page. Uses that extraordinarily powerful new formula, the one that says that we simply take -b and divide it by 2a. So our b is 2, -b is -2. We divide that by 2 times a. Our a is 1, so we're just dividing it by 2. -2 divided by 2, well, that just gives us a -1. And then we've always got a formula for y. That's the formula for the graph itself. So I'm now going to take the -1 to find the y-coordinate of the vertex and simply plug it in. Notice those parentheses are there again, just like you did in your calculator, to ensure that the -1 is being squared. -1 squared is 1. 2 times -1 is -2. 1 minus 2 is -1. So that gives us our x and y coordinate for our vertex. We're now going to take this information and we're going to plot the parabola. Another happy parabola smiling at us. It's got a positive coefficient and it's looks like it's an upward opening parabola. So at this point you're thinking to yourself, this is powerful. This tells us where extreme values happen. We could call those maximums, we could call them minimums. It all depends on whether it's upward opening or downward opening. Now before we get too far into this problem, this is an interesting problem in that it really does a good job of modeling real life. So I'm going to read it to you. It says, the revenue earned often increases, then decreases as the price increases. So let's just look at that first sentence. The revenue earned often increases, then decreases as the price increases. Now, we're comparing two things, revenue and price. So the first thing I want you to think is, if you didn't charge anything for it, you may sell a lot, but this isn't asking that question. This is asking, what's your revenue? And if you're not charging anything, your revenue is 0. So you start right there at 0, 0. And similarly, there's a price after which no one's buying anything. There's a price so high that the revenue returns to 0 again because no one's buying anything. So first off, convince yourself that there's 2 places on the x-axis that this curve crosses. One at the origin and one some ways out on the x-axis. Now, this is a parabola, right? As more people buy it and the price goes up, that's going up pretty steeply. But there's a point at which, as you continue to increase the price, people are stopping buying the product in the quantity they were before. In other words, they're buying less as the price is going up and the revenue starts to go down again. So this is a downward opening parabola. Now, something else that's going on here is the notation that we're using. And what we're using with our variables. So let's take a look at the second sentence. It says the revenue in thousands of dollars, so make sure your answer is in thousands of dollars, is a function of the price in dollars. So there's a new mathematical word. You see that throughout math and the sciences and business and anything like that. The function. So I'm going to introduce function notation here in addition to some variables that I think you'll agree were good choices. So it says that we're going to find the price that maximizes the revenue and the maximum revenue. So there's 2 things going on here. There's the price, we're going to call that P, and there's the revenue, we're going to call that R. And we expect the revenue to start at 0, go up to some peak at the vertex, and then go back down to 0 again when the price is so high no one's buying anything. So here's our formula. This is a downward opening parabola. I know that because the coefficient of the squared term is negative. And that makes sense. It goes up and then down. Well, that's the definition of downward opening. It says find the price that maximizes the revenue and the maximum price. This is a function, and this new notation here is brand new. So if you've been trying to do other things while listening to this video, pay really close attention for the next few seconds. This notation is not going away. It's so powerful that we use it throughout math and the sciences. The parentheses around the P after that capital R do not mean multiplication. They're not a grouping symbol. They are none of the uses of parentheses you have seen before. This is a brand new use of parentheses. This is function notation. It does not mean to multiply. It is not the base for an exponent. It is not a grouping symbol. This is function notation. It's read of, which is even worse, because of is how we say multiplication. So in a few seconds, you're going to hear me say R of P. Now, if you've been paying attention in a math class, you know from early days, from fractions, you know that of is a key word for multiplication. So you're hearing something that sounds like multiplication. You're looking at parentheses, and it looks like multiplication, but it is not multiplication. It's a way of reminding yourself what price you're talking about. So when we plug in a particular price, we're going to put it inside of parentheses there, but it is not being multiplied. It's a reminder of the price that we plugged in. So we're interested in finding the vertex. We're interested in finding the maximum value here, the price that maximizes the revenue. And of course, that's the vertex. So to do that, we're going to say negative b over 2a. That's exactly what we've been doing. Negative b, well, there's our b, 128. Negative b makes that into negative 128. We're going to multiply 2 times a, or a is negative 8. We do the arithmetic. I did this with a calculator, and I got that the price should be $8. So it looks like the price that maximizes the revenue is $8. Well, that's great, but what's the maximum revenue? And now that new notation is going to come into its own. So make sure that when you look at this equation for the first time, you see that we're using this function notation. This means the revenue when the price is 8. And rewind that and go over that again if you need to. That's the revenue when the price is 8. It's not multiplication. It's not the base for an exponent. It's not a grouping symbol. It's saying that I'm plugging an 8 into my equation for revenue. And you'll be given that. This isn't a business class. I'm not going to make you make up that equation, or calc class. So I'm going to plug it in, just do some arithmetic, and out popped 512. Now 512, remember, is the revenue in thousands of dollars. So that's actually about $500,000, a little bit more than $500,000. That's $512,000. Now, not a lot new here. You saw the vertex in the previous case. You know how to substitute a number into an equation. Really, the only new thing here is this function notation. And at this point, if you're willing to accept that there's a new use of parentheses that doesn't mean anything like what parentheses have meant before, it's a notation for saying the revenue when the price is 8 in this example, then you're in good shape. Let's look at one more of these. We go through it a little bit quicker. The questions are all set up the same. They look the same in my open math. The revenue in thousands of dollars is a function of the price in dollars, and there's that function, that equation. The revenue as a function of the price is negative 22 times p squared plus 132p. Again, it says find the price that maximizes the revenue and the maximum revenue. So the first thing we're going to do is find the vertex. That's negative b over 2a. So we're going to go grab our b, 132. We're going to change its sign, negative 132. In the denominator, we're going to multiply 2 times a, 2 times negative 22. We do some arithmetic, and out pops $3. So the price that maximizes the revenue is $3. So let me point out what that means. If you raised the price to $4, your revenue would go down. If you lowered the price from $3 to $2, your revenue would go down. It is the price component of the vertex. Now we also want to find the revenue. So we know that p equals 3. So wherever we see a p, we substitute in 3. So we do some arithmetic, and out pops 198. Remember, that's interpreted as thousands of dollars. So that's about $200,000 in revenue. Okay, our last example in Chapter 9 of using the vertex. So I call this timed kick. You could call it hang time. It's exactly that, though. Say you kick a ball, and it disappears above the horizon. You can't see how high it got. If you're interested, send me an email. I've got lots of videos of this with classes. We've gone out on the field. We've kicked balls. We've timed it. We've made videos, all sorts of good stuff. So this really is what it says. We're kicking a ball. We want to see how high it gets. To do that, we need a formula, and that formula is based on the strength of gravity at the surface of Earth. So here is our formula. And notice that I've written this formula in function notation. So that h of t, and I did say that correctly, it sounds like multiplication, but it's basically saying what is h for this value of t. That h is chosen for the height, t is chosen for the time in seconds. Now, there's lots of ways of computing negative 16. It's the acceleration due to gravity. It's related to the acceleration due to gravity at the surface of Earth. It actually comes from a calculus equation. You can derive it, and we do that in class when we have the time to do that. So there's our negative 16. That comes from the fact that we're on a nice-sized planet. We've also got our v sub 0. That may be new notation to you, the idea of putting subscript. Now, v is velocity, and we've talked about velocity all semester. Velocity is just the speed. But the speed of this ball, and you can imagine anything thrown or kicked or launched or thrown out of a trebuchet or anything like that, its speed decreases as gravity is pulling it downwards, and then its speed decreases downwards as it returns to Earth. So that v sub 0 is not all the speeds. It's not a variable. It's the initial speed, the speed at time 0. So v sub 0, some people in sciences and some of my colleagues in math will say v naught, where that naught is referring to the 0. And similarly, we've got lots of heights. This thing goes up and then it comes down. But we've also got h sub 0, h naught. And that's the height at time 0, the height at which you start the stopwatch when you're timing the flight of this ball. So there's our equation. There's a lot in it, and we've got a lot of work to do. So let's take a look at the setup of this question. A ball was kicked from a height of 3.3 feet. So let's deal with the 3.3 feet first. That was the height it was kicked from. So that's actually the initial height. So h sub 0 is 3.3 in this particular example. It was in flight for 1.8 seconds. Now, this is an extraordinary thing. Take a look at how we write that. That actually tells us two pieces of information. It tells us that after 1.8 seconds, the height returns to 0. So this is kind of your first test of being able to interpret function notation. H of 1.8 is 0. What's that saying is that the height after 1.8 seconds is 0. That's two pieces of information. T is 1.8, h is 0. So a lot is going on in that relatively short sentence. It was in flight for 1.8 seconds. H of 1.8 is 0. We're going to need that information. Now, we can take our general equation for the flight of anything that's kicked or launched, basically anything that's not propelled on its own, just given some initial momentum and then it returns to Earth. We're going to take that equation and we're going to plug in h sub 0, that 3.3. So you're going to see exactly the same general equation. The only thing that will have changed is that h sub 0 becomes 3.3. So here it is, just a little change right there at the beginning. Now, there's still too many unknowns, h, t, and v sub 0. So the first thing we've got to do is find how fast that ball was kicked. Now that's an extraordinary kind of thing to realize, that you can compute just from timing how long a ball was in flight before it hit the ground. And that is how fast it was kicked. And that's actually the first question we're going to answer. And we're going to do that with algebra, a little arithmetic, and we're going to use the fact that it was in flight for 1.8 seconds. Remember, that's telling us two pieces of information. So let's say, what happened after 1.8 seconds? So notice all the t's have become 1.8s. So if that looks like substitution to you, you are exactly right. That is substitution. 1.8 is taking the place of t. Everything else is the same. Now, you might say, okay, fine, t became 1.8, but remember that after 1.8 seconds, the height is 0 again. So in this next step, I'm going to do two things. I'm going to do a lot of arithmetic, but take a look at the left side. Take a look at what happened over there. That 1.8, when we plugged it in for the height, became 0. Now that makes sense. The height after 1.8 seconds is 0. Now the other thing that happened, of course, is a bunch of arithmetic. Now, what does that mean? That means we multiplied negative 16 times 1.8 squared and we added 3.3 to it. So you do that arithmetic almost certainly in your calculator and you get negative 48.54. The other thing that I've done is cleaned up how we're showing the multiplication here. There's no reason to show the coefficient after. That looks confusing to me. So I rewrote that term with the v sub 0 in it with the coefficient first. So there's 1.8 v sub 0. Now this is a linear equation. All we have to do is get the v sub 0 by itself, and there's only two things that have to go. We have to get rid of the constant term as we work backwards through the order of operations, and then we have to get rid of the coefficient. So I'm going to do exactly that. I'm going to add 48.54 to both sides, and then I'm going to divide both sides by 1.8. So amazingly, just by timing how long this was in flight, we know that it was kicked at 26.97, yeah, let's say about 27 feet per second. So we know the speed it was kicked at. We should say that this is the instantaneous vertical velocity. This is only the component going straight up and down. We rarely kick balls straight up in the air. So there's also a horizontal component, but that's not important for this course. What I'll be asking you is the initial vertical velocity, just that vertical component. That's what I'm going to call V sub 0. So our V sub 0 is, well, 26.97. And if you're wondering about that 26.97, I'm showing this in exactly the same way that I do in my open math. That is rounded to the nearest hundredth. So whereas I usually say leave the exact value on your calculator, here you're going to have to clear it. When we use V sub 0 again, when we use the initial vertical velocity again, we're going to have to enter 26.97. Now we're doing good. And what do I mean by that? We've now taken an equation that had three variables in it, ht and V sub 0, and we've now gotten rid of one of them. We know exactly what V sub 0 is. It's 26.97. So our equation is now down to two variables. Time is telling us height. So you can plug in any time you like here. If you get a negative height, it means that you've exceeded the flight of the ball. If you get something in between, you're talking about where it is up in the air. We're interested in finding where it reaches its maximum height. That's a vertex question. So negative b over 2a. Remember, our b was our initial vertical velocity. There it is once we've changed its sign. And amazingly, in the denominator, we've got the acceleration due to gravity, 2 times negative 16. So we do a little arithmetic, and we learn that it reaches its highest point after 0.84 seconds. And again, I've rounded to the nearest hundredth. You're going to be asked to do the same thing in my open math. So 0.84 seconds, it reaches its maximum point. Now that's all very well and good, but remember what this question was. It said, what is that maximum point? How high does it get? Now we've got an equation for that. We just found the velocity, so we're going to plug it in. And I'm going to use function notation again. So here is the height after 0.84 seconds. So wherever we see a t, we substitute in 0.84, and we get a lot of arithmetic. Notice that's entirely arithmetic. The only thing going on there is arithmetic. So we put it in a calculator, and out pops, after we've rounded, 14.67. Again, we're rounding to the nearest hundredths. So there's the maximum height. This got to about 14.5 feet, and that's as high as it got. Okay, one more of these timed kick questions. They are pretty cool to think that without a lot of information, we're able to figure out how fast it was kicked upwards, when it reached its maximum height, and what its maximum height was. When we take a look at this question, we notice that it's very similar. It says that a ball was kicked from a height of 2.3 feet. That's going to tell us our h sub 0. It was in flight for 4.5 seconds. Well, that's going to tell us that after 4.5 seconds, its height returned to 0 again. So we're going to go through exactly the same steps again. So taking that generic equation, we substituted in h sub 0, that initial height, the height it was kicked from. And then we're going to substitute in what we know about the length of its flight. That is, we're going to ask the question, what happened after 4.5 seconds? So notice that t is now 4.5, so all sorts of good substitution took place. T is becoming 4.5. And that includes in the function notation itself, h of 4.5, that is the height after 4.5 seconds. And we know what the height after 4.5 seconds is. It's 0. So that left side is about to become 0. The right side, yep, out comes your calculator because you've got to do a fair amount of arithmetic over there. Take a second to do this. It's amazing how often students forget how to enter something in their calculator correctly. So make sure that you can get that negative 321.7 as the constant term. Now we're working backwards through the order of operations. We want to get the V sub 0 by itself. So as we work backwards through the order of operations, we're going to undo that subtraction. No great surprise. We're going to add 321.7 to both sides. To get the initial vertical velocity by itself, we're going to divide by the 4.5. So there's, and of course it's rounded to the nearest hundredth. So there's our initial vertical velocity, 71.5 feet per second. This probably was propelled. That's really fast. 1 second, 71.5 feet. I'm doubting this was kicked, but in some way it was propelled vertically upward. Now, 4.5 seconds does not sound like a long time, but in terms of something falling and being propelled upwards, it really is. So the next part of this question is finding where that vertex is. So we take our equation, the one we were working with a few seconds ago, and we say, hey, we know what v sub 0 is now. So when we recopy the formula for the height of this particular ball, we put in the 71.49, taking the place of v sub 0. Now we're going to say, well, when, meaning what time, did it reach that vertex? And of course, negative b over 2a is going to answer that question. There's negative b. And in the denominator, the acceleration due to gravity at the surface of Earth, approximately. And it looks like we get 2.23 seconds, again, rounded to the nearest hundredth. So after 2.23 seconds, this ball, whatever's being projected, reaches its maximum height. Now we know everything about this equation for this particular ball, so we're going to say what's the height after 2.23 seconds, which means we're going to plug in 2.23 wherever we had a t. Notice that there are no variables over there. This is a job for your calculator, and it looks like I got an answer of 82.16 feet. Remember, rounded to the nearest hundredth. And that completes Chapter 9. That completes everything new from between Math 100, Beginning Algebra, and Math 120, Intermediate Algebra. So I hope you enjoyed that and are getting ready for the exam.